Hey everyone, and welcome to my channel. Okay, so today we have an absolutely fascinating explainer lined up for you. We're going to unravel what I like to call the billion-dollar AI mystery. We are thoroughly in the age of AI right now, but beneath all those flashy headlines about the newest chatbots and generative models, there's this massive hidden inefficiency just lurking in the very data centers powering all these systems. We're talking about literally billions of dollars of the most advanced supercomputers on Earth, fundamentally bottlenecked. But there's a brilliant piece of open science from DeepSeek that just might have solved the whole shebang.
So there's a single, kind of shocking number right at the heart of this entire problem. 40%. That's it. Despite tech companies spending billions upon billions of dollars, scrambling to buy every single advanced GPU they can get their hands on, these incredibly powerful supercomputers are sitting at an abysmal 40% utilization rate when they're running complex, agentic AI tasks. Think about that for a second. That means 60% of the time, the hardware you just spent a total fortune on is effectively sitting idle. It's just waiting around. Now, if you want your AI to answer faster, your first instinct is probably, well, just buy more compute power, right? But the crazy reality is, adding more compute actually doesn't make it faster. To understand why, we've got to look at how an AI actually thinks.
All right, let's dive into this using a really brilliant analogy from Dr. Carlos Onlai over at 2-Minute Papers. Imagine you're reading this massive, thick book, but every single time you turn the page, you instantly forget all the characters and everything that just happened. Literally, a blank slate. So to be able to even understand the next page, you'd have to go back and completely reread the entire book from the start. That is exactly what happens in practice with AI. As the analogy goes, assume we have a huge brain the size of a mountain, but there's a fatal flaw. Information is coming into that brain through a tiny straw. We're spending all our money building a bigger mountain, but we completely ignore the straw. So the AI ends up spending all of its time just slowly rereading old information, rather than actually doing any new thinking.
And all that reading happens in something called the KV cache. You can think of the KV cache as essentially the AI's short-term memory. The absolutely crucial point here is that modern multi-step AI agents, the ones solving those really complex coding or research problems, they are what we call I/O bound. That basically means they're constrained by input-output memory speeds, not by their actual processing power. Get this, in a typical multi-turn conversation, the AI model reuses about 98.7% of its prior context every single turn. And that average context length? A massive 32,700 tokens. Meanwhile, it's only generating maybe 400 new tokens. So the AI is literally choking on this tiny memory straw, spending the vast majority of its time desperately trying to reload its massive short-term memory just to remember what it was doing in the first place.
And honestly, the terrifying part is that this problem is getting worse. Over the last few hardware generations, spanning from NVIDIA's Ampere architecture all the way to their new Blackwell GPUs, we've actually seen a 14.4x drop in the I/O to compute ratio. So what does that actually mean for us? It means the graphics cards got insanely, massively faster at doing the actual computing math. But the memory bandwidth, the speed at which the data can be pulled out of storage, it just did not keep pace at all. We built a much, much bigger brain, but the straw stayed the exact same size. This hardware mismatch is the absolute root of our 40% utilization nightmare. Now, this hardware mismatch cascades directly into the physical layout of a modern AI data center. Today, large-scale systems use what's called a disaggregated architecture. That's just a fancy way of saying it splits the work between two completely different types of machines. On one side, you have the prefill machines. Their job is to read all that massive KV cache data. And because of that, their network straws are completely jammed. Totally saturated and choking on data. But then on the other side, you have the decode machines. These are the ones actually generating the new text. And guess what? Their network straws are almost completely empty. Their storage interfaces are just sitting there, largely unused, while the prefill machines are dealing with a complete and total traffic jam.
Which brings us to DeepSeek's incredibly clever solution, beautifully titled DualPath. When faced with this whole mess, DeepSeek didn't just say, hey, let's build another multi-billion parameter AI model to solve it. No, they recognized this for what it was, an infrastructure problem. They realized they didn't need a bigger brain. They needed to build a bigger straw. DualPath is just an absolute genius infrastructure detour. It's a complete re-architecting of how data physically flows through the data center network to completely bypass this massive bottleneck.
So here is exactly how this clever detour works, broken down into 3 steps. Step 1, instead of forcing the prefill machines to do all the heavy lifting and reading, DualPath tells the decode engines to use their totally idle storage bandwidth to read the KV cache from storage, right? Put them to work.
Step 2, the decode engines then grab that massive memory file and send it over to the prefill engines using the data center's ultra-fast RDMA network, which stands for Remote Direct Memory Access. And finally, step 3, the system dynamically schedules this load on the fly. It's constantly balancing the work based on real-time network conditions. It's essentially taking a super-fast back road to completely bypass a massive highway traffic jam.
But wait, you might be thinking, taking a massive detour on the high-speed compute network, doesn't that just create a whole new problem? I mean, if we push massive memory files onto the exact same roads the AI uses for its high-speed thinking, we're just going to create a brand new traffic jam, right? Well, DeepSeek completely foresaw this. To fix it, they introduced a brilliant NIC-centric or network interface card-centric traffic management system. They essentially set up strict traffic control on these high-speed roads. The thinking traffic, which is that latency-sensitive model execution, gets absolute, undeniable priority. Meanwhile, the memory traffic, all that heavy KV cache loading we talked about, acts like background work. It only gets to use the leftover, unused space on the network. This guarantees that the detour never, ever slows down the actual AI calculations.
And guys, the payoff of this detour is absolutely incredible. Before DualPath, those multi-million-dollar GPU clusters were hovering around that sad 40% utilization mark. But after implementation, utilization rockets straight up to 80%. This is an absolutely insane jump, especially coming from a single infrastructure paper. DeepSeek essentially figured out a way to get effectively twice as much work out of the exact same multi-billion-dollar hardware that data centers already own. No new GPUs required whatsoever.
And when you translate that raw utilization into actual performance, it means an average speedup of 1.96x for online serving throughput, almost twice as fast. And crucially, this 1.96x metric fundamentally proves the entire hypothesis of the paper. It proves that storage bandwidth, not pure compute power, was the dominant bottleneck holding back our most advanced AI systems all along. By simply widening the straw, the entire system immediately doubles in efficiency. It's wild.
Now, I do want to keep us grounded here for a second. As amazing as this whole thing is, it's really important to understand exactly what this is and what it isn't. This is highly situational. It is a deep, infrastructure layer optimization designed specifically for massive data centers. It is absolutely best for long context workloads. We're talking 32,000 tokens or more, like complex coding assistants, multi-turn agentic workflows, and scenarios with high KV cache reuse. So what is it not for? Well, it's not a magic bullet that's going to make your short, single-sentence Q&A prompt run twice as fast on your personal laptop. It specifically accelerates the absolute hardest, most complex situations where AI typically slows down to a complete crawl.
Which really leaves us with this incredible realization. DeepSeek didn't patent this, they didn't close it down, and they didn't keep it some secret corporate weapon to dominate the market. They published the paper and released this as a free, open-source gift to the entire world. And honestly, that is the true power of open science. Because this is technically boring infrastructure plumbing and not some flashy new AI model, it might not dominate the mainstream news headlines today, but by solving the billion-dollar memory bottleneck, DualPath quietly paves the way for a future where running highly complex, deeply intelligent AI inference is drastically cheaper and faster for everyone. It signals a complete paradigm shift, from AI being purely about raw compute power to being about how brilliantly we can move data around.
And that wraps up our deep dive explainer into DeepSeek's DualPath. It definitely leaves us with a massive, provocative question. As open science continues to outmaneuver trillion-dollar monopolies with pure infrastructure genius, what other massive bottlenecks are just sitting out there, waiting for a clever detour? Let me know your thoughts down in the comments below. If you enjoyed this explainer and you love breaking down the hidden mechanisms reshaping our technological future, please hit that like button and subscribe to the channel so you don't miss our next breakdown. Thank you so much for learning with me today, and I'll see you in the next explainer.